Okay, today we're talking about atoms and models of atoms and things like that. And so for the problems, we're going to look at some calculations here. I think all just concerning hydrogen atoms, since they're the nice simplest ones. And so consider a hydrogen atom in its n equals 3 state. All right, so we have on our equation sheet these different states for a hydrogen. This is all for a model for a hydrogen atom. And so we have the ground state down here, n equals 1, 2, 3, 4. So we have different states. And so we're saying we're up here in the third level. All right. And so it says what size is it. And so what size is it? That's talking about what is its radius, right? And so I guess we can call it R3 because it's in its third state. So what makes a hydrogen atom be bigger than a different hydrogen atom? It's because basically it's where its electron is orbiting. So we have the proton in the middle, and then we have the electron in some state going around, right? So in the ground state, it's closest in, n equals 1, and then it comes out a level, and then it could be out here. And so we're talking about n equal 3 state, so it would be out to the third level, whatever. So this would be R3, right? And so the bigger the state number is, the larger the radius. And we have equation on our equation sheet here. Let's see, where are we? So in general, we have Rn, where n is the state, is n squared, Planck's constant squared, 4 pi squared, Coulomb's constant, the atomic number, mass of an electron, and the charge of electron squared. So we have all this stuff in there. For hydrogen, all these are constant, right? Except for the state. And so we can say Rn is n squared over R1. And so we call it the Bohr radius for R1. So it's like all this in here is R1. And we can just use this. Unless the problem says to calculate it, we can just go ahead and use the number 0.529 times 10 to the negative 10 meters. So again, a very tiny little thing. And so R3 in this case, then, we said we're using the Rn is n squared R1. So is n squared R1, which is 3 squared times R1, which is the Bohr radius, 0.529 times 10 to the negative 10 meters. Did I copy that right? Yes. I remember it right. Okay. All right, so just plugging in. 3 squared times 0.529 e negative 10. 476 times 10 to negative 12, or we could say 0.4, no, 4.76 times 10 to negative 10, yes. Anyway, meters. Okay, so that's the radius, average radius kind of thing of a hydrogen atom in n equals 3 state. Okay, so when it's asking for size, we can assume that it's looking for a radius is a good answer to what is the size. All right, part B. What is its ionization energy? All right, what does ionization energy mean? Ionization energy means how much energy does it take to make the hydrogen atom an ion, right? An ion is something that's missing or gained electrons. And so in this case, it would lose an electron, right? It's ionized, it's lost an electron. So basically it's saying how much energy does it take to pull our little electron we're talking about here in this little random cloud, whatever, however it's moving about. How much energy does it take to pull it out? Right? And so let's go ahead and calculate it. So we want to get E3, so it's the energy of the level. And so we could just read it off our handy dandy equation sheet. We should get 1.51 electron volts. But let's go ahead and pretend like we didn't know that was there. And so our energy level, we can also calculate it here. And so this is for, the first part is for Oh yeah. So for hydrogen-like atoms that have only one electron circling around, right? It may have different number of protons, um, but then we have over here for hydrogen, then it's this negative 13.6 over n squared electron volts. So negative 13.6 electron volts over n squared, where n is now 3, so it's negative 13.6 electron volts over 3 squared. So, and let's say, well, let's go ahead and calculate in electron volts, and then we'll also calculate it in joules. So we got 13.6 divided by 9. So 1.51, which is what we just said it was on our negative 1.51. All right, so that's so how much energy does it take to release it would be the positive 1.51. So this is energy of the atom in the state, just like we calculated there. And so we want to say how much energy has to come in to release it. It would be the opposite of that. And so E ionization, I guess, is 1.51 electron volts, or convert it to joules. So E ion joules, 1.51 EV times 1 EV is 1.602 10 to the negative 19 joules. 1.51 times 1.602 e negative 19. Much uglier number, right? So E ion in joules is 242 times 10 to the negative 21 joules. All right, for part C, what frequency of photon to get it to n equals 4? Okay, so if we're going to shine some light on it and try to get it to jump even further out to n equals 4, right? How much, well, we need to know kind of how much energy it takes, and then what kind of frequency of the photon would make that happen, right? And so does it take more energy? Does the photon, so it says in or out, so is the photon actually getting released by the atom because it's giving up energy and it's losing energy to go to 4, or is it gaining energy to go to 4? And so that means then the photon, a light would have to come in and give the atom more energy. All right, and so looking at these energy numbers, where does it have more energy and where does it have less? It has the least energy in here, right? Because it's negative 13 versus up here it's at 0, right? So to get up here to have more energy, we were talking about going from 3 to 4, right? We would have to give it energy to get it to come out a little bit further, right? So we have to put in positive energy. We have to shine light on it at a certain frequency to get it to go up a notch, right? And so it is, the photon is coming in, right? Energy coming in, photons coming in, versus if it was going down, say, to 2, I think we're going to do that later, going down to 2, then it loses energy and could give off light or give off a photon. Okay, so right now, going from 3 to 4, and we're going to, 3 to 4, and so it's going to take in some energy. So E photon, so photon comes in, right? Energy of a photon is HF. Yes, we're looking for F, so we'll use that version. And so E photon, and that's going to equal the energy difference of the atom, right? And so the atom is going from, so we want delta's final minus initial, so final is level 4 and initial was level 3. Okay, and so we're looking for F, so we can just rearrange this. So F is going to be E4 minus E3 over H. E4 we can plug in here 4, or we can, I think it's on our sheet, negative 0.85 is E4, negative 0.85 minus negative negative, where we have right here, 1.51 over H, 6.626 seconds. This up here was, both of these are electron volts, so we got this problem between electron volts and joules. And so we do have, if we're wanting to do things in electron volts and Newton meters, we could use that equation. Do we want that? We're not doing, let's just do it the hard way, I guess, because we're not talking about lambda and such, and it's good practice. All right, so again, 1 electron volt is 1.602 10 to the negative 19 joules. The electron volts cancel, joules cancel. We end up with 1 over seconds, which is what hertz, what frequency should be, which is hertz. Okay, so let's get our F is negative 0.85 plus minus 1.51. Let's put that in parentheses. Times 1.602 e negative 19. And that's the whole top. Let's put some more parentheses just for fun. And divided by, only thing on the bottom is H, 6.626 e negative 34. Okay. So F is 150. 160 times 10 to the 12th hertz. Is that terahertz? I think so. Okay. High frequency. High frequency. Frequency of a photon. All right, so that's the frequency of the photon. Part D. What wavelength the photon is emitted? Sorry. Going to n equals 2. So we're going to assume that it means starting back at 3 and going to 2. So electron goes from 3 to 2. And so the atom is going to a lower energy state. So it's going to lose electron. Or, I'm not lose electron. It's going to release energy, lose energy. Let's just say atom releases energy. All right, let's go of a certain amount of energy, and we can see it as a photon. If it's in the visible spectrum kind of range, we could see it as light, right? Okay, so we kind of got the same equation now. So delta E, at this time, we would expect it to be negative, right? We got E, the final is E2, and the initial is E3. And this will be now equal to the photon that comes out. So it's also going to be equal to HV, but it's the opposite direction, right? But let's go ahead and calculate this. So E2, and we could put in negative 13.6 over 4. Let's just do that. 13.6 divided by 4. So we get negative 3.4 minus E3, which was the negative 1.51. And again, let's just verify. Yes, negative 3.40. Good. And so we get negative 3.4 plus 1.51, negative 1.89 electron volts is how much energy the atom is giving up. In terms of the photon, it's the energy the photon gets it's energy of the photon as it leaves, right? So E photon is equal to 1.89 eV. Let's put that into joules. So 1 electron volt is 1.602 times 10 to the negative 19 joules times 1.602 e negative 19. And so we get 303 times 10 to the negative 21 joules. All right. And then what is it asking us for here? Wavelength. All right. So E equals HF, but also equals HC over lambda, which we're looking for lambda, so we'll use that version. And so lambda, multiply through by lambda, divide through by E, and so it's going to be HC, I'm trying to make that be a big C, but it should be a little c, over E, photon. So that's 6.626, 10 to the negative 34 joule seconds, 3.0 times 10 to the 8th meters per second, speed of light, divided by our energy for this photon, which was 303 negative 21, which is calculated for joules. So our wavelength then is 6.626 E negative 34 times 3E8 divided by 303 E negative 21. Okay. 656 nanometers, 10 to the negative 9 meters. All right, so is that on our, oh, I don't have a spectrum here, but I think that is in the visible spectrum. I can find something that has a spectrum picture on it. Here we go. And so 656, somewhere in the orangish kind of range, looks like there. Okay. So that is D. Yep, that looks like it for day 37.